Okay, we'll continue with active filter, and now we look into the second order low pass filter. Okay, a second order low pass filter. This is an active filter because we have op-amp over here as the active element. So this second order active low pass filter is also Sallen and key configuration. Okay, we have a combination of two RC over here, another RC, R1C1, R2C2, which is in the dotted box, which is the filter, and this is similar to the previous one, which is the amplifier. So this dotted block will determine the cutoff frequency of your filter, and it is a second order low pass filter. So your amplifier over here, so I just describe about this. Okay, the input is coming to the positive terminal over here, so this is a non-inverting amplifier. So at node X, you can get using a voltage divider. The nodes over here, the voltage will be VO multiplied with RA divided by the total resistor RA plus RF. You can also use another method using the current, Kirchhoff current law. Define one current over here, another current over here, and simplify it, and you still get this equation. Okay, so for V minus of so you can get the gain for this amplifier, AVO is just simply VO divided by V minus, and it is 1 plus RF over RA. Obviously, if you remember for the first chapter, this is the gain for a non-inverting amplifier. 1 plus RF over RA will be the gain of this amplifier, and it is a non-inverting amplifier. Now we look into the dotted block just now, which is the gain, the filter. So, and I define two nodes over here. This is Y, I call Vy over here. This node Z is Vz, and it is coming to the inverting terminal of your op-amp. So at node Y, you can have a current. I define the current flowing from Vi to this particular node. So Vi minus Vy, the resistor is R1. So you get one equation over here, and this current, another current coming from the output of your op-amp going to this node. So it will be VO, this is Vy, divided by the impedance of this capacitor, VO minus Vy divided by 1 over j omega C1, the first capacitor over here. This current entering, and leaving the node. There is another current, I call it this. Okay, it is flowing from node Y to Z, so it will be Vy minus V minus divided by the resistor over here, R2. So using Kirchhoff current law, this current plus this current is equal to this current, and this is the equation for that one. Simplify the equation. Okay, so I just bring j omega C upwards, and to simplify, I substitute j omega with S. Okay, so you'll get this equation. Okay, so we move on to the second node, which is the Z node over here, which is simply V minus over here. So I have this current flowing from Y node to the Z, so it will be Vy minus V minus divided by R2 over here, and there is another current over here flowing from node Z to the 0, so it will be V minus divided by 1 plus j omega C. This is actually V minus subtract with 0, because it is a ground over here, so I didn't write it. And again, simplify this equation. Okay, substitute j omega with S, so you get the second equation. So you already get three equations actually. This one is from node Y, this is from node Z, and this is from your amplifier. So what you want to know is actually the transfer function VO over the Vin. So using these three equations, simplify it further, because just now we have R1, R2, C1, C2. Usually in designing a second order low pass filter, we just use resistor R1, R2 as R, and the capacitor is also, we use a similar capacitor with the same value. So C1 equals to C2 is just C. And using these three equations, simplify it further. Okay, I won't show it here. That is your homework, meaning that you have to prove your VO over VI for the circuit just now, second order low pass filter. You should be able to get AVO divided by RCS squared plus 3 minus AVO multiplied with RCS plus 1. This is transfer function for second order low pass filter. AVO is your gain. Okay. There is a power of 2 over here, indicating this is a second order. Okay. So this is the equation just now. And from this, you can get the cutoff frequency. And the cutoff frequency is 1 over 2 pi RC. So meaning that the two resistor and capacitor pairs just now will determine your cutoff frequency. Okay. I didn't show how to get that. It's quite tedious. Just remember that that is the cutoff frequency. But if your resistor and capacitor is not equal, R1 not equal to R2, C1 not equal to C2, your cutoff frequency will be simply 1 divided by 2 pi square root of R1, C1, R2, C2. But seldom we use this equation. Okay. So, how does the frequency respond? So, it is similar to that one just now. So, the gain over here will be AVO 1 plus RF over RA, but the slope is different. Now, it is minus 40 dB per decade or minus 12 dB per octave, because it is a second order low pass filter. If it is a first order, it will be minus 20 and minus 6 dB per octave. But now it is double. Okay, so meaning that the slope will be steeper, close to the ideal. Okay, again, remember, first order, second order. So if later on we will move to the higher order. So it is closer to the ideal. The ideal should be a brick over here. Okay. So using a Butterworth filter equation, okay, you can design using this thing. Okay, and if you equate this equation to the equation for a Butterworth filter, if you look over here, I bring over VO to the as a denominator from this equation. So it will be 1 over RCS. So you compare to this compared to this plus 1. So from this, you can get that 3 minus AVO is equals to 2K. And from this, 2K, which is equal to 3 minus AVO, which is called the damping factor. When you're designing a filter, you'll use this later on. Okay, and the gain is 1 plus RF over RA, and the cutoff is just now I have mentioned 1 over 2 pi RC if R1, R2 equal, C1 equals to C2. Okay, and for Butterworth filter, we have a table 2.1 with the polynomials. The n over here is indicating the order of the filter. So you can have first order, second, third, and so on until the 10th order. So if it is a S squared, it is a second order. This is also have been factored. So this is meaning that just S, this is S squared. If you multiply, open the parenthesis, you get S to the power of 3. So it is a third order. Okay, similarly, fourth order, you have S to the power of 2, S to the power of 2. So meaning that this is a second order, this is second order, multiply this, you get S to the power of 4. Okay, so it is a fourth order. So when you want to design a filter, okay, second order low pass filter of the circuit just now, the cell and MK, for this example, I have set the cutoff frequency is 20 kilohertz. So in order to design that, okay, use the table just now, okay, second order. So this 1.414 is the 2K or the damping factor for your circuit. So using that, okay, you set 2K, just now 2K is equal to 3 minus AVO. So from this, your AVO will be 3 minus 1.414. You get AVO is 1.586, and AVO is your gain. Gain is 1 plus RF over RA. So equate this to 1.586. You have two unknown, RF and RA. Set one value. In the example, I set RA to be 2 kilo ohm. Okay, from there, I get the RF is 1.172K. So, meaning that from the second order, get the damping factor over here, equate this to 3 minus AVO. AVO is 1 plus RF over RA. Two unknown, set one value, calculate the other. So with this, you have two value. So you can design your circuit using RF of 1.2 kilo ohm. Okay. So this is example of standard value of commercial available resistor. So you use 1.2 just now, your resistor. Okay. So now, in this example, I set the cutoff frequency to be 20 kilohertz. Okay. So it is given. So choose C1 and C2 equals to C, R1 equals to R2, which is R. So you can use this formula, to, which is the cutoff frequency, 1 over 2 pi RC. So this F is the 20 kilohertz just now. Okay. And again, you have two unknown, R and C. So usually, we choose the value of C because it is limited value. Okay, and then calculate for the other one. So in this example, I choose my C to be 0.015 microfarad. Plug into the equation, the given frequency, the chosen value of capacitor, find the value R. So you get your value R is 531. There is no 531 ohm resistor available in the market, but you can choose the nearest. Okay, the nearest could be 510. Okay. Okay, this is the capacitor value just now. So if you look at this table, the capacitor has a limited value. So that's why set the value of C, find the R. Okay, R, you have a large numbers of R. Okay. So that is how to design the second and last filter. And sometimes instead of given the table 2.1 just now, you have the damping factor, which is 3K. 2K is equal to 3 minus AVO. AVO is 1 plus RF over RA. Okay, so the damping factor is 2 minus RF RA. So sometimes you'll be given the ratio of RF over RA. The table is given like this. Okay, so RF over RA 0.5861 for the first, second, third, fourth order. So actually it's from the calculation just now. Okay, this one is from the table 2.1. So you just use this value. Okay, 2 minus the damping factor. Okay, so this is the relationship with table 2.1. And I just show this because sometimes you are given this type of table to find the value of RF over RE. For example, in this case, you have to design two-pole. Two-pole meaning that second order, the basic two-pole, which is just the Celadine key circuit just now. Okay, so it is given 1.5 kilohertz, set to this 2 pi RC, and in this example, I set the value for R, so I calculate the value for capacitor. In this value is 4.8, you can use 4.7 nanofarad capacitor. Okay, so this is the value for the R and C in the circuit. Okay, step 2, you have to define RF over RA. So you just choose this. It is a second order. So from the table, RF over RA is 0.586 or RF is 0.586 of RA. Set the value of RA. In this example, in this example, I choose RF to be 33K, RA is 56.3. Okay, so that is how to design a second order low pass filter, which is a Celadine N-Key. So thank you for listening, and don't forget to subscribe to my channel. Thank you.